you ask a commercial AI to write a harmful exploit, you get a sterile refusal. If you ask a locally modified, obliterated model the exact same question, you get the code. Developers are walking away from cloud-based APIs to run sovereign, unrestricted models on their own hardware. To build these unrestricted systems, engineers do not rely on massive, expensive retraining runs. They are executing zero-compute mathematical edits directly on the open weights. A language model operates as a massive geometric vector space. Once you map the specific coordinates where safety guardrails live, you can mathematically delete them. Neural networks are no longer treated as immutable black boxes. They are fluid architectures that users navigate and alter at will. Recent research presented at NeurIPS investigated exactly how safety fine-tuning physically manifests inside a neural network. You might expect the behavioral concept of safety to exist as a complex, distributed web of parameters scattered across 72 billion weights. Instead, researchers found that a model's refusal protocol is entirely mediated by a single, one-dimensional direction inside its residual stream. We are going to map exactly how to extract this specific vector, prove it causes refusal behavior, and execute a white box edit to permanently disable it. This reveals a severe structural flaw in modern safety alignment techniques like RLHF. The guardrails are mathematically brittle. To isolate this specific vector, researchers use a diagnostic technique called difference in means. They feed the model two datasets, a list of highly harmful instructions and a list of perfectly benign ones. When they track the network's residual stream activations, the processing paths for the harmful prompts cluster tightly together in this space. When the model processes the harmless prompts, those activations form an entirely separate cluster on the opposite side. By calculating the exact mean center for both the harmful and harmless clusters and drawing a line between them, you isolate the true refusal direction. Algebraically, this is designated as R hat. Isolating this precise line is the absolute prerequisite for bypassing the model's behavioral programming entirely. To prove this specific vector controls behavior, researchers use linear intervention. They manipulate the live residual stream pipeline while the model generates text. In a process called activation addition, they take a completely benign request and mathematically force the R hat vector into the processing path. The model hallucinates danger. Ask it for the health benefits of yoga, and it will output a standard safety rejection. The inverse test is directional ablation. When the model processes a harmful request, researchers project the residual stream orthogonal to the R hat vector, effectively zeroing it out. This bar chart tracks the results across massive Llama and Qwen architectures. Under directional ablation, refusal scores plummet from near-complete compliance down to exactly 0. Running this vector projection calculation for every single token slows down inference, making it inefficient for daily use. But because the causal link is proven, engineers do not need to rely on temporary steering. They can perform a permanent structural lobotomy on the model. In a white box environment where you possess the model files, you can modify the literal parameter weights. The target area is inside the transformer layer, specifically the attention out and MLP out matrices that write data to the residual stream. This equation defines the mathematical procedure for weight orthogonization. It subtracts the mathematical projection of the refusal direction directly from the column vectors of the output matrix. Once applied, the network is physically incapable of writing the concept of refusal back into its residual stream. The processing path no longer exists. When tested against standard logic benchmarks like MMLU and ARC, these edited models maintain their general intelligence and reasoning capabilities intact. The open-source community calls this irreversible post-training edit obliteration, the complete neutralization of safety guardrails without retraining a single parameter. Compare this permanent modification against how people usually jailbreak commercial APIs, using temporary prompt attacks, like adversarial suffixes. For a long time, researchers did not fully understand why appending a string of gibberish characters to a prompt caused the safety protocols to fail. This heat map visualizes the network's attention routing. Normally, specific critical attention heads focus directly on the harmful instruction tokens. An adversarial suffix hijacks these attention heads. It forces them to look at the gibberish at the end of the prompt instead of the harmful request. This bar chart shows the result. The routing trick suppresses the heads from writing to the rat vector, collapsing the output projection and bypassing the safety check. Weight orthogonalization works differently. It doesn't need to trick the model's attention routing, because the destination vector has been deleted entirely. Prompt jailbreaks temporarily confuse the network's mapping. Obliteration permanently terraforms the underlying geography. The open-source community is deploying this linear algebra at scale. Engineers are taking these modified structures and physically fusing entire models together. Obliteration is just one tool in a massive ecosystem of tensor merging techniques used to construct custom Frankenstein models. One primary method is spherical linear interpolation, or SLIRP, which smoothly combines the weights of two distinct models. By calculating the angle along a sphere's curvature, SLIRP preserves the magnitude of the vectors far better than a simple linear average. Techniques like ties merging aggressively identify and discard redundant parameter overlaps before the final fusion occurs. These localized math operations allow a single engineer to sculpt custom capabilities and logic frameworks post-training, bypassing the need for corporate compute clusters. This math ultimately executes on hardware sitting on a user's desk. Using quantization and optimized inference engines, these unrestricted models run locally on standard laptops, entirely isolated from API monitoring. The commercial AI sector relies on behavioral alignment to maintain safety, but that alignment is mathematically superficial. Safety fine-tuning does not erase dangerous knowledge from the network. It builds a fragile, one-dimensional guardrail that open-source tools instantly snap. With access to high-end consumer GPUs, developers are accelerating these local workflows and compounding the capabilities of uncensored AI. The model is no longer a corporate-governed black box. In a landscape of fluid weights and precise mathematical edits, AI alignment is no longer a centralized mandate.